So, what we will look into is basically as I was telling you, earth energy balance, right, because whatever energy is received by the earth, it comes mainly from the sun. So, whatever is received annually is also dissipated out annually. Daytime it receives radiation, night it actually back to the cosmos. Besides that, the seasonal variations are there. So, that this shows a kind of a bookkeeping or accounting of the earth energy scenario, right, and that is what the diagram was, that is what I was looking at in the last class. So, what we said is 100% is what is received, out of which 50% goes right to the atmosphere, absorbed by the particles in the atmosphere, and some of it comes as diffused radiation to the ground, right, and it is reflected back. So, some of it is reflected back, some directly reflected from the diffused particles itself, the sky, I mean atmospheric particle itself, and then 50% is received onto the ground, out of which some percentage goes direct reflection from the ground itself. So, if you look at that 50%, 5% gets direct reflection from the ground, 40% reflected by, absorbed by the atmosphere or reflected back, 20% goes as long wave radiation to the sky, like as you can see this one long wave radiation, and 20% would be evaporation from the sea, moisture, etc., right. So, this is again now 50% what is received on the eye, this is what is the breakup, basically long wave radiation about 20%, evaporation from the moisture front, sea and such things another 20%, and convection radiation back from the surface of the earth another 10% or so on. So, that is what it is. Anyway, this is not really very, we need not go into further details of it, but we understand that. Now, the radiation that falls onto the ground, right, basically if it is coming directly normal to the surface, normal to the ground surface, the intensity will be highest. But if it is coming inclined, same amount of energy is falling on larger surface area. And as you can see, for example, the normal surface is B, C is the surface area which is onto the horizontal plane or to the ground, then C, if I have incident angle as cos theta or cos beta as we are calling it. So, B is equals to B will be basically I C, or I can write it in this manner, there is a pen available, right. So, for example, I B is a beam radiation that is falling into an area of B, and I C is the radiation on the horizontal surface, on the C surface, multiplied by C, area C, right. Area C is the, let us say C is this area, C is this area, I mean width is 1 I can take. So, C into 1, similarly this is B into 1. So, this should be same because energy is same, intensity of radiation is defined in watt per meter square, that is what I told you other day. So, watt per meter square multiplied by the meter square, they should be same. Now, what is B by C? B by C is cos beta. If this is this incident angle is defined normal to the surface, this rays makes, that is what we call as incident angle normal. So, this is incident angle actually which is same as this, right, this is incident angle. So, this is same as this. So, basically it is I B cos beta, right. So, because the area on which it is falling is large. So, this is so normal incident radiation is higher, intensity will be higher, then inclined any time if there is incident angle is more than 0, this would be less, radiation received will be less, right. Now, how do you define incident angle? Normal to the surface and the ray, angle between normal to the surface and ray, that is your incident angle, right, normal to the surface and ray. Now, since this is normal to this, right, this is normal to this, and this one is normal to, this one is normal to the ray. So, this is normal to the this one is normal to the ray, so angle between these two will be again beta. That is what I was just telling you. Now, solar constant is the amount of radiation that is available on top of the atmosphere, right, because atmosphere absorbs. So, amount of radiation that comes on top of the atmosphere, that we call as solar constant. This varies a little bit. This varies a little bit because sun's position, distance of the sun from the earth is not same, it is elliptic orbit. So, perigee, epigee and all those. So, there is the slight variation. Besides that, sun itself, its quantity of radiation emitted by the sun, that also varies somewhat, but approximately one can take is something of the order of around 1395 watt per meter square. Some other book you might find slightly different and so on. So, that is called solar constant, that is received on top of the atmosphere, right. Now, that is what I was saying, 2% variation in output of the sun's output is itself varies, and 2.5% due to distance, but we do not care about it really, we are not interested in this, we are trying to understand only. Okay. So, that is what it is, right, and that is what it is, top of the atmosphere it is more, and distance travelled here is less compared to distance travelled in this position. So, obviously absorbed will be more. So, it will depend upon, and normal surface obviously intensity will be higher compared to inclined surface. So, these are the issues, atmosphere, etc., etc., this is the issues. So, that is what it is. So, 2% variation, that is what I said, I already said that. So, that is again the similar kind of diagram, 50%, 5% straight away goes out, 20% is radiated from the atmosphere, diffused radiation goes back, cloud, etc., 25% absorbed there, 23% comes to the ground, diffused radiation. The radiation, what is diffused radiation, what is specular and diffused? You see, if I have a mirror, then rays will be reflected back, right. So, beam and reflected beam. Now, angle of incident is equals to angle of reflection, that is specular on a polished surface. But if I have a matte surface, something like paper or your wood, etc., etc., it will actually, it will not be radiating, it will not be reflecting the way that is written, that is shown here. The pen color I should change, actually try to change the pen color, or maybe it is changed somewhat. It will be actually reflecting in all direction, you do not see your image, and mirror you see your image back, but on table or something like that you will not see your image. So, that is what is happening, all getting scattered in all direction, and if it diffuses in all direction, there is a completely diffused surface, right. So, diffused radiation, here it gets absorbed by atmosphere and diffused in all direction, 23% comes as diffused radiation from the atmosphere, 27 is a direct radiation, and this is what actually it also dissipate over the year. So, that was related to the the initial discussion of ours, and then we will continue with from here itself. So, temperature we have already talked about, this affects dry bulb thermometer in shade, we talked about sky condition. So, wind speed and direction, this we already looked into the factors which affect the environment surrounding the building, solar radiation. Now, how do we measure also we talked about, I just did not mention about this one, this is called pyranometer, which measures radiation. A pyranometer measures radiation. Now, there are varieties of type. The one conventionally been used is we will have a blackened, oh, this color is not black anyway, blackened sensing device, right, blackened surface. There is a dome, concentric dome, there is one dome, glass dome here, there is another dome there, and it has got a heavy base, just a small quick understanding, there is a heavy base is heavy mass. This is black, and actually my color is not showing really black properly, it should be black, or let me see if I can come close to the black, or it's got all erased. Anyway, so this is blackened surface around this, so which I will have, maybe this was better black, okay, does not matter. So, it's something like this. There are two concentric domes, there is a sensing device here and a heavy mass there, and you have actually what is called thermocouples in series, right. So, basically the hot junction is here, cold junction is somewhere in the heavy mass, and there will be number of them together, series of them, right, such that temperature difference between these two can easily be sensed. So, when radiation comes in, it is absorbed in that blackened portion and temperature rise occurs there. This is a heavy mass, heavy thermal mass, so its temperature would not change. Besides that, it is also covered by a disk, so that it does not receive radiation. So, base does not receive radiation, it has got a heavy mass, its temperature will remain same, but the blackened sensing area, it receives radiation. So, the difference in temperature, which is actually kind of magnified or summed up, because there are a number of hot junctions and cold junctions, that is dependent upon intensity of radiation. So, it can be calibrated. These two glass domes are put in to reduce down the convective heat transfer. Also, glass traps the radiation, so no radiation back can go, right. So, two of them will ensure that there is no formation of eddy or current flow, air movement, etc., is minimal. So, that is a pyranometer. Anyway, again the instruments are not really of our, and rainfall gauges are there, so that you know. So, we talked about this sometime earlier. So, these are the parameter, and humidity, of course, as I said, absolute terms, moisture vapor per unit kg of dry air, that is how I do. So, that is what we said, amount of moisture that can be held in temperature, relative humidity, measurements of relative humidity. I already talked about that hygrometer last class, or difference in dry and well bulb temperature, in saturated condition dBT minus WBT is equals to 0. This is just a repetition. Solar radiation measurement I already talked about. So, now this is the environment around, right, but this environment is not constant. This environment changes from what we call season to season, location to location, as well as season to season, because the environment is mainly governed by the sun's radiation. That is what we are talking about, the energy that comes from the sun. So, sensible heat is actually measured by temperature changes, which you can sense. Latent heat is one which occurs because of phase change. Latent heat occurs when moisture is vaporizing, that is latent heat. So, since it receives energy, sensible temperature change would occur, sun's energy is coming. So, temperature, surrounding temperature or environmental temperature around the building is a function of the energy received from the sun. Besides that, we have seen the moisture will evaporate, so moisture content, relative humidity, etc. So, all are related to that, and it varies from, therefore, since sun's radiation is not constant every day, whatever I get over a period of time, let us say month of July and August to December, if there is a, there will be difference of sun's radiation, because sun, the sun is, the earth is revolving around the sun. So, therefore, its position of this particular location with respect to the sun, it will go on changing. Similarly, depending upon North Pole, for example, it receives radiation, indirect radiation also, not direct beam radiation, never it receives there, because beyond 23.5, beyond certain latitude, it does not. So, it is important to look into sun earth relationship to understand this temperature and relative humidity on those parameter, environmental factor, variation of those factors, right. That causes what we call seasonal variation, right, seasonal variation, and rotation of the earth about its own axis causes what is called diurnal variation, daily diurnal variation. So, we are trying to look into that sun earth relationship, then we will understand, then we can come to the climate. So, if you look at sun earth relationship, right, basically earth has got a banking, it is inclined, it is inclined to this plane of revolution, right, plane of its revolution around the sun, that has got a banking, and that is constant all the time. Approximately 23.5 is the this this angle can be 23.5. So it's got a banking. I think it's written somewhere, exact somewhere it will be there. So it has got a banking. Now it is revolving like this, revolving all the time like this. So some point it will be normal, some other, and this plane on which it is normal will keep on varying. So we can find out an angle between the equatorial plane, which is equator, this one diameter, equatorial diameter, the center. This is north, this is south pole. So normal to that is a diametrical circle, which is equatorial circle, and sun's rays on particular day falls normal to this point, and as it revolves around, only at 2 point of time this is normal to the equatorial diameter, right. So this is around 21st December. You find that it is normal to 23.5 southern latitude. Now what is latitude? Latitude is the angle at a given location. So I have a chord circle, I have a chord circle, I have a chord circle here. So from the center of the earth, if I join a line, the angle that will make with the chord circle, that we call as latitude. So latitude of North Pole is 90 degree. Latitude of North Pole is 90 degree. Latitude of equator is 0. So that's how we vary this latitude angle. So latitude angle varies. So location of the place, or point, I mean location on the surface of the earth, any geographical location, I can express it in terms of its latitude. Longitude is the other one, which is this kind of, I can divide the whole approximately spherical earth into 360 degrees or 180 in east direction and 180 in west direction, right. So 360 degree, and divide them into equal angles, this 360 complete circle. So these are longitude actually, and if you travel from little bit of digression, have you, any one of you read a book Around the World in 80 Days by H.G. Wells, Phileas Fogg? Well, just digression. Basically, he had a bet, and some club in England, he had a bet that I will complete the world, go around the world and come back to London in 80 days. And he managed his way through a long story. It's a book, it's a novel sort of scientific, science fiction sort of thing. So he moves around, even India comes in there. So he moves around and then finally reaches there, and according to his watch he found that he is 1 day late. Then he suddenly realized, as he was traveling, he should have changed his time. He should have changed his time. He did not do that. So he counted 1 day more. So if you are moving, moving from east to west, you have to adjust your clock, because when it is 12 noon here, let us say in Delhi, it will be morning somewhere in Europe and so on. So you got to adjust, right. He didn't do that adjustment, and then suddenly realized at home, he saw the calendar and his servant or somebody has marked it the previous day. Ran to the club, of course won the bet. That's the story. So anyway, coming back to this, so longitude relates to time. What do you call? Solar time and standard time. Standard time is, Indian standard time is with respect to 82.5, that's the longitude of Allahabad, right. So far it's like that. So coming back to this, as you are saying, longitude, we will have a little bit talk about that sometime later on also. So latitude defines the position of a location on the surface of the earth with respect to equatorial diameter in terms of the angle. So sun's rays falls normal to, because it has got a banking, this is 90 minus 23.5 is how much? 0.5. So this banking is 66.5, since it's got a banking with this plane of revolution 66.5. Therefore it falls normal here sometime, normal here some, normal to this equatorial plane only in 2 times, that's 21st September and on 21st March. This is around 21st June, summer solstice and winter solstice and so on. equinoxes, these are equinoxes. So, suns, suns, I think this is, this diagram also shows you vernal equinox, winter solstice, autumnal equinox and summer solstice. So, it falls normal to this circle which is 23.5 latitude north on summer solstice, that somewhere around June. This is winter, somewhere in Australia you will have summer during that period of time. So, sun's radiation falls normal here, and during this autumnal and vernal equinox it is normal to the equatorial plane. So, normal beams radiation can be received only from 23.5 to 23.5, I mean north to 23.5 south. So, that is why these places will have relatively warm environment, right. So, what you do is we classify all the latitude into 3 groups, say 0 to 30, 30 to 60 and then 30 to again 30 north to 30 south, right, and 30 south to 60 south and 60 to 90, that would be right. So, the one from 60 to 90 they are polar climate, subtropical, and 30 north to 30 south we call it tropical climate, because the environment is warm and I have not possibly defined climate. Climate is the pattern of temperature, relative humidity, etc., at a given location, right, and weather is the daily data, daily changes. So, weather relates to daily temperature, relative humidity, etc. So, when we say today's weather is likely to be rainy, we mean, but then we talk of monsoon season. So, climate, seasonal variation depends on the climate and everything is related to a sun. So, that is what it is, right. So, that is what we looked into. Even wind flow pattern is because of sun's radiation, because during the summer solstice the sun's radiation will be normal to Tropic of Cancer, that is 23.5 north, that we call as Tropic of Cancer, and sea around 23.5, it passes through India, by the way, Ahmedabad, close to Ahmedabad, and I think Agartala. If you draw a line from Ahmedabad to Agartala, 23.5. Indian latitude varies from 8 degree north, Thiruvananthapuram, somewhere around that place is 8 to about Delhi is 29, it is 29, and 33 or so, something like that, J&K, that place. So, it would be Ladakh, or those areas would be of this order. So, this is by and large India is tropical. Now, even the wind movement is dependent upon the sun's radiation, because when in summer solstice around that period of time it will be heating up the sea around the Tropic of Cancer. So, the hot tropical front will start moving up, the hot air gets heated up, water vapor, so air gets heated up, and basically as it heats up, the cool air from the subtropical region will tend to move to fill in this gap, and then it will move, this circulation pattern actually, pattern starts. So, this is tropical front, subtropic height, subtropic front, etc., and polar height. So, this also is because of the wind movement, is because of this. So, but there is a slight modification will be there, if moving upward, but the earth is rotating. So, what you call Coriolis forces. So, you find the patterns are something like this, this is the direction shown as seen from vertically from the top. So, that is what it is. So, they are called trade winds actually, because the tradesmen in sea, they are the first one to recognize this pattern of this wind. Anyway, so wind variation, air movement, wind velocities at a given location is also related to the climatic scenario, or its location and kind of solar radiation it receives at latitude and so on. Altitude is another factor. At higher altitude, at sea level, the radiation is less. At higher altitude, it can be somewhat higher because of the distance that we talked about, absorption by the atmosphere, etc. And this is solar altitude angle. That means when it is falling normal, this is the maximum, when it is normal. So, depending upon the solar altitude angle, we will define what is the altitude angle of the sun a little bit later on. So, that is what it is. So, height also varies. So, therefore, at higher altitude you are likely to receive somewhat higher radiation, but does not mean this will be warmer, because there are other factors which makes it cooler. One of the ways of finding out, of course, all this data are available from meteorological department. There are stations and they measure this, all data could be available, but one can even do a little bit of for understanding purpose, one can look into some sorts of equation and try to look at how you can calculate it out from solar constant. We know the solar constant value. So, you see it is like this beam radiation ISC stands for solar constant multiplied by a factor kT. kT is given as, this is more for understanding, but if data is available, let us say for New Delhi data is available, design data is available, then you do not bother to look into this, but we understand how it is. For example, kT is this factor which is a function of Tu is the turbidity factor, m depends upon m is equals to 1 at sea level for vertical radiation, right, and this depends upon altitude, this is a turbidity factor, depends upon whether it is industrial or non-industrial, how much pollution, etc. So, m is 1 at sea level for vertical radiation with Tu equals to, let us say 1.8, which is big, depending upon turbidity it can go to 8, value of around 8 or so, one can find out how much the radiation would be. Same for a location of 1000 meter altitude, this m value would change, m value will depend upon the distance, right, altitude of the location, and this is depends upon turbidity. So, if you know solar constant, this is kind of an empirical formula, 0.9 into m, which is a function of the altitude, Tu is a function of atmospheric pollution or turbidity there. The tabular values are given. For industrial situation, this value is higher. What it means is 0.9 into fraction to the power some value, right. So, if you increase that value, what will happen to kT value? It will reduce 0.9 into some power, 0.9 to the power 2 is 0.81, if it is 3, that much multiplied. So, the value is high for polluted environment, industrial situation, and this again depends upon distance, right, this depends upon distance. So, that is how it is. So, one can, these typical calculations are shown here, right, these typical calculations are shown here. Okay, this m values, like these values are all tabulated, so one can actually find it out. Now, this, if I want to find out the radiation, so what we have seen is, let us look at these parameters a little bit more and let us quantify them, then we will define the climate classification of tropical climate and so on. Let us understand, we define certain angles. Supposing I want to find out how much radiation is falling onto a vertical surface or a horizontal surface, wall of the building or roof or inclined wall or whatever it is, then two things I got to know: current sun's position, its intensity of radiation, sun's position relative to the surface I am interested in, right, and all these are done in angular measurements or extension into spherical trigonometry. So, we define certain angles. For example, sun's position can be defined, I can define the position of the sun in the sky vault by two angles. One is called an azimuth angle, other is the altitude angle. Now, what is an altitude angle? I think this diagram gives you. For example, this is the sun, let us say this is my vertical surface, but this is my horizontal plane, this is the horizontal plane, this is the horizontal plane, right. This angle is the altitude angle of the sun. If I take sun's projection onto the horizontal plane, the angle the sun rays makes with its projection, we call it altitude angle, right. I am denoting here by beta, right. I hope I will be following the same notation. If there is a change, just correct me. So, this is called altitude angle of the sun. Now, that that has nothing to do with the wall so far. Now, I also want to define the position in the sun in the sky world. So, what I do, I take a reference plane in the horizontal plane, I take a reference direction. So, let us say I can take north direction. So, if I take north direction, then the angle the sun's ray, projection of the sun ray on the horizontal plane, the angle that projection makes with the geographical north, it could be, I can call it azimuth angle and measure it clockwise. Well, this is one convention. I can start from south and measure clockwise. So, I can I have to follow the same convention throughout. Equations changes when you, because some books, for example, maybe people in southern hemisphere would like to follow a different convention than people in northern hemisphere. So, some book you will find that they are actually taking it from north, some might take from the south. But whatever it is, azimuth angle is the angle between reference direction and projection of the sun ray onto the ground. In this case, it is shown as phi with respect to south. So, phi is SOH. So, SOH is taken with respect to south clockwise. It could be with respect to north also. So, the formula we use, one has to be, you must know what are you using, right. So, that is what it is. So, these are two angles which defines the sun's position. Now, I must define the position of my surface. So, what I do? I draw a normal to the surface. I draw normal to the normal to the surface. I draw a normal to the surface. Okay, let me erase out the previous one. So, I think this is, otherwise will confuse. So, this is normal to the surface. Now, I can find out wall azimuth from the same reference, or if it is from the south going clockwise, anti-clockwise, then it will be minus. So, wall azimuth, right, wall azimuth. Wall azimuth means I draw a normal to the surface and angle between my reference direction and this normal in horizontal plane. If it is an inclined surface, I will take the projection of the normal onto the horizontal plane. For example, if this is tilted, if it is somewhat tilted, I take the normal, take its projection onto the horizontal plane and its angle from a reference direction, angle between this projection and the reference direction, that is the wall azimuth, that is wall azimuth. So, wall azimuth, and angle between this normal and the sun's projection, sun's rays projection onto the ground, that we call as wall solar azimuth. What is wall solar azimuth? The difference between the angle between the wall azimuth and solar azimuth, the angle between the normal, right, to the surface or its projection onto the ground and projection of the sun's ray onto the ground, that is we call as wall solar azimuth. So, wall solar azimuth, he is calling it as gamma, which is, of course, whatever convention you follow, it will remain same, because you will start from same reference both the times. So, this is how we define wall, right. But I have another angle for the wall or surface to be defined called tilt angle. If it is vertical, wall solar azimuth, and wall azimuth defines its position, wall solar azimuth defines its position with respect to sun. But if it is an inclined surface, then I have something called tilt angle. Tilt angle is the angle that surface makes from with the horizontal, tilt angle, right. So, that is tilt angle. So, that is how we define a surface, that is how we define. So, these are solar altitude. Okay. Zenith angle is 90 degree minus altitude angle of the sun. Zenith angle is with the vertical, the sun's ray is making angle, the angles the sun's ray is making with the vertical, that we call as zenith angle. So, solar altitude, zenith angle, wall azimuth I have defined, solar azimuth I have defined, and wall azimuth I have defined. Now, one more angle I should define, relationship with respect to vertical surfaces and sun's ray, incident angle. What is the incident angle? Incident angle is the angle between the sun ray and normal to the surface. So, incident angle will be, if the normal, if it is inclined surface, inclined surface, suppose the surface is inclined, its normal will be something like this, sun's ray is something like this. So, angle between this two we call it incident angle. So, for a tilted surface, incident angle will be in vertical plane, it will not touch the horizontal ground. But for vertical surface, that incident angle is basically the normal to the surface, that is my this to this ray, this is what is incident angle, right. So, these are the definition of certain angles which are important for our discussion, and I think that would be required. So, this is shown again just to make it clear, no confusion should be there. So, this is the sun, this is the solar altitude angle, this is the solar azimuth angle again taken from the south here, right, and sun moves from east to west. So, it will change from time to time of the day, both azimuth angle and altitude angle of the sun, it will change from time to time of the day. And obviously, it will vary from day to day also, we will see that, because for example, you consider 23.5 on north latitude, on 21st June, around that June date whatever I showed you earlier, 23rd June or whatever it is, the sun's ray is normal, that means at 12 noon it will be sharp right at the head, but in December it will be somewhat inclined. So, you see this angles will keep on varying day to day and as well as time of the day. So, we will see that how we take account for this. I think I have another diagram showing the same thing. This time this is from the north, this time you see the reference is north, this is the azimuth angle of the sun, sun moves from east to the west, right, and sun moves from east to west, and it is inclined towards the south actually, northern hemisphere, and altitude angle is this, azimuth angle is this. So, I think this concept should be clear now, there should be no confusion on this. So, azimuth angle is the angle between sun ray projected on horizontal surface with a reference direction true north measured clockwise, could be what we will be using most of the time in our equations, that we will be using true north clockwise. Altitude angle, angle between sun ray, and we will be using a notation phi, and altitude angle, angle between sun ray and projection to the horizontal surface, okay, right. And then wall azimuth I have already defined, angle between reference and projection of normal to the wall on horizontal surface, and incident angle, angle between sun's ray and normal to the wall, right. Wall solar azimuth, as I said, angle between projection of the normal to the wall on horizontal surface and sun ray projected on the horizontal surface. So, I think this should be clear, this angle should be clear, right. So, incident angle is the angle between sun's ray and normal to the wall. So, at this point I think I have defined this all. So, angles we have defined. Now, next we can follow how do we calculate out this angle, how do we estimate these angles for any point, we will do that.